The symbol d by dx represents the operation of differentiation. There is something strange about this symbol. It is sometimes treated like a variable. For example, x squared means multiplying the variable x by itself. In the same way, d by dx is sometimes squared too. However, its meaning is different from that of squaring a variable. This represents taking the derivative twice. It's called the second derivative. In practice, the parentheses are often omitted, and it's written like this. Still, these notations are a bit strange. There are several other strange similarities between derivatives and the variable, but we'll come back to those later. Now, a certain question arises here. Given a variable x, we can consider differentiation with respect to x. In the same way, we can consider differentiation with respect to x, and then differentiation with respect to that differentiation itself. In other words, differentiation of differentiation. Of course, this is a rather suspicious idea. We can write such a symbol, but its meaning is unclear. Let's think about this a bit more specifically. This is the power rule, one of the most well-known formulas in differentiation. When differentiating x to the n, the result is n, x to the n minus 1. Here, we are describing differentiation with respect to the variable x, but with some tweaking of the formula, could we describe differentiation of differentiation? So first, let's represent d by dx using a capital D. Writing just d might make it look like a variable, but it actually represents the operation of differentiation. Here, let's forcibly replace x with d in the earlier formula. This gives us the following. Now then, does this equation have any meaning? At first glance, it looks like a familiar formula, but its meaning is shrouded in mystery. D to the n does not mean raising a variable d to the power of n, but rather represents the operation of taking the nth derivative. And here we are differentiating with respect to d. In other words, we're differentiating the nth derivative operator with respect to differentiation. You're probably not sure what that even means. Is this equation actually correct? What does it mean to differentiate with respect to differentiation? It doesn't seem like we're just finding the slope of a tangent line. To solve the mystery, we'll need some clues. Start by closely examining the relationship between differentiation and the variable. Something should become clear. Now, I'll leave the rest to my other self from here on. I can't find Metan anywhere. I heard she was spotted in this forest though. It's gotten pretty late today, so I guess I'll just sleep here for now. Huh? What's this?
Zundamon.
Metan, I just heard your voice.
I'm glad you came, Zundamon. This is the world of dreams.
Yes?
I've been trapped inside this world. To rescue me, you have to solve this mystery.
Whoa, what on earth is this? What is this even supposed to mean? The differentiation symbol and a variable are connected by an arrow.
This is a difficult problem.
I don't even understand what the problem is.
This problem is telling us to examine the relationship between differentiation and the variable.
Wait, is that what it means? You're pretty good at understanding things. Well, at least I've got the situation figured out.
You catch on quickly.
Thanks. But still, when you say the relationship between differentiation and the variable, I'm not really sure where to even begin looking.
Well then, how about trying to differentiate the variable itself first? In other words, differentiating x with respect to x. Do you know the answer to that?
I think it's 1.
That's exactly right. By the way, since the derivative of y with respect to x is written as dy by dx, the derivative of x with respect to x can be written as dx by dx.
Yeah, that makes sense.
Differentiation is defined using limits, but intuitively dx represents a small change in x, so dx by dx expresses the ratio of x's small change to itself. It kind of makes sense that the answer is 1.
Yeah, when you put it that way, I guess it does.
Also, you can write the derivative of x with respect to x, like this too.
This is a way of separating the operation of differentiation from the thing being differentiated.
Differentiating a variable with respect to itself gives 1. This gives us some insight into the relationship between differentiation and the variable. Let's go further. Now we will denote d by dx by a capital D from here on.
Whoa, that's a pretty interesting equation. It almost looks like it's saying d times x equals 1. If we divide both sides of this equation by x, we get something like this. So that means d is the same as 1 over x.
That's certainly an interesting way to look at it. But something is missing.
Why is that?
This equation mixes things from different worlds. D represents the operation of differentiation, while x is a variable. More precisely, it's the function y equals x. In other words, a function that maps x to itself. And the right-hand side, 1, represents the constant function y equals 1.
So, since dx doesn't actually mean d multiplied by x, we can't just divide both sides by x like that.
Unfortunately, that's the case. As it stands, something is missing. Oh, looks like Morty has come. Zundamon, I'll leave the rest to you.
Huh? Oh, right. I was in a dream, and I was chasing some strange mystery. Metan got trapped in the dream world. Is she still stuck there now? This is bad. Right now, Metan and I exist in different worlds. Different worlds? I feel like I heard something about that earlier. I'm pretty sure we were following the relationship between differentiation and the variable, and we arrived at this equation. Well, it's just that differentiating x gives 1. Here, d and x exist in different worlds, so it seemed hard to get anything more meaningful out of it. This is a tricky situation. Let's try drawing it out for now. D and x exist in different worlds. As it is, there's a limit to how much I can explore their relationship. But if I could bring one of them into the other's world, I might discover a new kind of relationship. Alright, let's give it a try. First, let's think of d in this way. D maps the function f of x to another function f prime of x. And in the same way, let's think of x as mapping the function f of x to another function, x f of x. In other words, we treat x as an operation that multiplies a function by x. Strictly speaking, this x is not the same as the original variable x, but for now, let's use the same symbol for both. By the way, the function that maps x to f of x is simply written as f of x here. Similarly, the function that maps x to x f of x is simply written as x f of x, so keep that in mind. Now, since both d and x map one function to another, we can say they exist in the same world. Let's try combining the two in this world. That should reveal a different kind of relationship between d and x. This d of x represents the composition of d and x. So, first we multiply the function f of x by x and get x f of x. And then we apply d to that. In other words, we differentiate it. In this way, d of x maps one function to another. Let's try actually calculating it. In this expression, we're applying d of x to the function f of x. D of x means applying x first, then applying d afterward. Since d represents differentiation, we just need to differentiate x f of x. In other words, we need to calculate the derivative of the product of x and f of x. When differentiating a product, we take the derivative of each part and add them together. First, differentiate x, then differentiate f of x. Differentiating x with respect to x gives 1. So the first term becomes f of x, and the second term is x multiplied by the derivative of f of x. We can express that using x of d like this. That definitely represents differentiating first, then multiplying by x. To sum it all up, it turns out like this. On the left side we have d of x, and on the right side we have x of d. This turned into a pretty interesting result. We can now move the x of d term to the left-hand side. That gives us something like this. Now let's factor out f of x and rewrite the left-hand side in this form. Technically, we should define what this subtraction means, but for now, let's just say it's okay to write it this way. So, we can think of d of x minus x of d as something that maps f of x to itself. If we use the commutator, we can write it like this. It represents the difference between d of x and x of d. The commutator of d and x maps f of x to f of x itself. Let's just write this as 1. Since multiplying by 1 doesn't change anything, this notation is sometimes used. And with that, I've obtained a relationship between differentiation and the variable. The commutator of d and x equals 1. In other words, the order in which d and x are applied makes a difference in the result. And that difference turns out to be 1. Normally, the order of multiplication doesn't affect the result. But in composition, the order really matters. That's kind of mysterious, isn't it? And so, we've uncovered the mysterious relationship between differentiation and the variable.
This is quite fascinating. Two things that should be completely different are somehow maintaining a strange kind of balance.
Feels less like we've solved the mystery, and more like it's gotten even deeper.
But if you think about it again, differentiation and a variable actually share some things in common.
What? What do you mean?
For example, when differentiating a sum of functions, you can differentiate each function and then add the results. This is called the sum rule, and it's similar to the distributive law. In fact, if you replace d by dx with x, the equation becomes almost the distributive law.
Yeah, you're right.
Also, when differentiating a function multiplied by a constant, you can bring the constant out front. Together with the sum rule, these are what's called the linearity of differentiation.
Wait a second. If we replace d by dx with x in this case too, yeah, the equation still holds. I see, maybe differentiation and a variable really are kind of similar. But of course, there are also lots of differences. So what's the fundamental difference between them?
There are many ways to answer that, but the one that's especially important this time is this.
Uh-huh. This is one of the well-known differentiation formulas, right?
That's right. This is the formula for the derivative of x to the n, known as the power rule, and it's one of the fundamental examples in differentiation. Now, what happens if we replace d by dx with x in this formula?
Huh? Well, for the left-hand side, it would look like this. But we can't use the right-hand side as is. This is basically x to the power of n plus 1. That feels kind of obvious. Wait, hold on a second. When you differentiate x to the n, an n appears as a coefficient. And that doesn't happen just by multiplying by x. Also, differentiation decreases the degree by 1, but multiplying by x increases it by 1.
Good observation. These formulas are asymmetric when it comes to coefficients, but symmetric in terms of the degree. Both change the degree by 1, but in opposite directions.
Now that you say it, it seems obvious, but I hadn't noticed it before.
Keeping this in mind, we can look at the relationship between differentiation and the variable from a new angle. When you apply d of x to the n, you first increase the degree by 1, then differentiate, so the coefficient becomes n plus 1. On the other hand, applying x of d to x to the n means differentiating first, so the coefficient is just n. In both cases, d lowers the degree by 1 and x raises it by 1, so the final degree stays at n.
This is a fascinating result. Comparing them, the first case gives a coefficient that's 1 greater. So if you increase the degree before differentiating, the coefficient becomes 1 greater. And that 1 shows up in the relationship between differentiation and the variable.
This is just an example using x to the n, but it's an important one to keep in mind. Zundamon, you're almost there. Keep it up.
Wait, what do you mean by that? I see. Mornings come again. Well, at least I've now gained a much clearer picture of the relationship between differentiation and the variable. By the way, what happens if we try to generalize this equation? What if I replace x with a function f? It feels like I could generalize the commutation relation. Now I'm curious. Let's give it a try. We're applying the commutator of d and f to a function called g. First, using the definition of the commutator, we get this. And we can expand it just like a normal algebraic expression. Now, let's think of f as an operator that multiplies a function by f itself. So, in the first term, we multiply g by f, then apply d. On the other hand, in the second term, we apply d to g first, then multiply by f. And the derivative of the product fg can be calculated like this. Here, only g is being differentiated. In the end, only f prime g remains. So, when you apply the commutator of d and f to g, the result is f prime g. In short, applying the commutator df means multiplying the function by f prime. It's almost as if d is differentiating f through the commutator. What in the world is going on here? Let's compare this with the original commutation relation. Maybe, just maybe, in that equation too, d differentiated x through the commutator, and that gave us 1. No, it's risky to limit ourselves to just one interpretation. But as one possible explanation, it might be valid. The mystery only keeps getting deeper. Whoa, it's gotten really late. I think it's time to call it a night. Metan. Hey, Metan! Huh? She's nowhere to be found.
Zundamon!
That voice. Metan. I'm right here. She can't hear me. Wait, am I trapped in a dream now?
That's the hint.
What? A hint? Where's the hint supposed to be? No, wait. Metan and I have switched roles. That must be the hint. If D differentiates x through the commutator, then, as a special case, we might be able to think of D as differentiating x to the n through the commutator too. Now let's try switching the roles of differentiation and the variable. In other words, let's raise D to the power of n instead of x. D to the n means the nth derivative operator. So how does x affect the nth derivative operator when viewed through the commutator? We'll start by calculating the case of the second derivative. Expanding the commutator gives us this. Since the second derivative means applying differentiation twice, we can write d squared as d of d. Let's insert an intermediate step. The two terms will cancel out. Technically, we should verify whether this kind of algebraic manipulation is valid in this context. But for now, let's just go ahead. Then we see the commutator of d and x appear here. We know that equals 1. So the result is 2d. This means, differentiate first, then multiply the result by 2. So the commutator of the second derivative operator and x is 2d. It almost looks like d squared itself is being differentiated. I can't believe it actually happens, but it does. I kept working through the calculations, and just as I hoped, the results matched my expectations. When calculating the commutator of the third derivative operator and x, the commutator of the second derivative operator and x appears, so we can reuse what we already worked out. Eventually, I arrived at this result. Taking the commutator of d to the n and x is equivalent to differentiating d to the n. You can prove it rigorously using mathematical induction, but let's set that aside for now. Just like d differentiates x to the n through the commutator, x differentiates d to the n through the commutator as well. Here, the roles of differentiation and the variable have completely swapped places.
Well done, Zundamon.
Metan! Pa? Did you end up back here? Oh well, I guess that's fine.
The mysterious relationship between differentiation and the variable. Let's explore its structure just a bit more. D and x have this commutation relation. Now let's define a new symbol bullet as the opposite of composition. In other words, we define A bullet B to mean B of A. Mathematically, this amounts to considering the algebra with reversed multiplication. So D of x can be rewritten as x bullet D, and x of d as d bullet x.
Wait, this has exactly the same structure as the original equation.
D and x have swapped places, and composition became bullet, but the structure of the equation is unchanged. In terms of the commutator, d and x play symmetric roles.
Really? Is that so?
Earlier, Zundamon, you derived the commutation relation between d to the n and x starting from the basic one.
Wait, how do you know about my calculations?
Actually, you can also derive the commutation relation between d and x to the n from that same basic relation.
Oh, I didn't realize that. But yeah, since d and x play symmetric roles here, it's not surprising that we can derive similar equations. I see. So that's the logic behind it.
As a side note, squaring d and squaring x may look the same, but they mean different things. That's because d squared doesn't mean squaring a variable. It represents the second derivative operator. But there's another way to think about it. D squared means applying differentiation twice, written as d of d. X squared means multiplying a function by x twice, which is the same as x of x. So in this world, squaring something can be seen as composing it with itself. This idea also supports the relationship between d and x. And of course, the same goes for general powers.
Now that you say it, that really makes sense.
Zundamon, this is serious.
Whoa, what's going on?
There's a strange operator deep inside the world of dreams.
What? This is... shift operator? Wait, what even is an operator again?
The meaning of operator can vary by context, but here just think of it as something that takes one function and turns it into another.
I see. So we've actually been working with operators. When you apply the shift operator to f of x, it shifts x by a.
Exactly.
But what are we supposed to do with this?
Earlier, we differentiated the nth derivative operator, so maybe we can try differentiating the shift operator, too.
I'm starting to lose track of what we're even doing here.
Then let's organize the situation a bit. We previously took the commutator with x to differentiate nth derivative operator. So in the same way, we can think of taking the commutator with x as a way of differentiating the shift operator too.
Oh, I see what you mean. That's a pretty wild way of thinking, but at least it seems like we can calculate this commutator. Alright then, let's try calculating the commutator of the shift operator s sub a and x. As usual, we just need to see what function the commutator maps f of x to. Let's extend the commutator. We get this. In this term we multiply by x and then apply s sub a, and in that term we apply s sub a first and then multiply by x.
This is the usual setup up to this point.
S sub a is the shift operator. It shifts x by a. In the first term, we're applying the shift operator to x f of x, so it turns into this. In the second term we apply the shift operator to f of x, so that part looks like this. These parts cancel each other out, so we're left with just af of x plus a. And using the shift operator again, we can write it like this. Okay. Applying the commutator of s sub a and x to f of x gives this result. Since f of x appears on both sides, we can rewrite this as an operator equation.
That's a pretty simple result. When you differentiate s sub a, it becomes a times itself. This looks familiar somehow.
Really? You think so?
Let's try writing s sub a as e to the power of ad, at least formally.
E to the ad? What does that even mean?
We're just writing it like that for now. Don't worry about the details.
I don't really get it, but okay. In that case, we can rewrite the result like this.
Yes, exactly. That's the idea. The counterpart to this equation would be a formula where d differentiates e to the ax through the commutator.
Oh, I see. Yeah, if you line them up like this, the two equations look totally symmetric.
Using standard derivative notation, the derivative of an exponential function looks like this. Note that b to the 0 is 1. These are the defining properties of the exponential function. As the counterpart to that, we can consider an equation where x is replaced with d. However, e to the ad isn't the exponential function but the shift operator, and differentiation here means taking the commutator with x. We're just borrowing the notation of exponentials and derivatives.
These equations may look almost identical, but their meanings are very different. By the way, what does e to the 0 equals 1 mean in this context? That's not referring to the exponential function, right?
That's right. Here, it means shifting by 0.
Shifting by 0 basically means doing nothing, so the result is just 1.
Looks like you got it.
To sum it all up, by following the relationship between differentiation and the variable, we arrived at the exponential form of the shift operator. Since d represents differentiation, this is what it means. And that gives us this equation.
That was an unexpected destination, wasn't it? Actually, this was kind of a backdoor approach. The shift operator goes much deeper than it seems. If you'd like to dive deeper into that depth, we've explained it in detail in this video. Be sure to check it out. Well then, take care everyone.
See you later.